All right, so we're talking about a particle moving. Well, we've already kind of talked a little bit about the direction of the particle. Then with that direction gave us really the velocity of the particle, how the particle is moving with an x velocity and a y velocity. But we'll also look at the acceleration of the particle and the speed of the particle. So different things that, are just describing motion, only now in 2 dimensions. Okay, and I'm looking at this particle moving in this direction given by this set of parametric equations. And I'm going to zoom in at this location. Okay, and what's going on? We can see the particle moving in this direction. If we looked at other positions, we could see it's going from kind of a downward right to an upward left. We can see it's moving left and up. But how quickly is it moving left and up? It's determined by, the derivatives or the velocity of the particle in the x direction. So dx dt. Well, dx dt is really actually the velocity of the particle in the x direction. V sub x is what I'm going to give you. And in this case, it's given by -3. It's just the derivative of, it's the change in my position with respect to time. Okay, and I can see kind of visually that -3 if I draw a horizontal line coming from my particle. And the -3 is kind of the length of this vector, this x direction vector. It's not going on forever and ever. It has a distance. It has a length. And then the particle has a y direction, and it's really a velocity in the y direction, v sub y, and it's given to us by 2t, and we can find kind of that at t equals 2, and I get 4. So the particle is moving up, and it's moving up this quickly. So this has direction and length. Well, if we kind of look at both of them together, this v sub x at 2 and this v sub y at 2, we can see a third vector, this velocity at a specific time vector. I'm going to say v sub t. And we can see the direction that we are traveling in. And this also has a length. This length is telling us how quickly we are moving in this direction. Okay, now v sub t we will typically express in terms of its x kind of velocity as well as its y velocity. But v sub t, which we'll say will equal some x velocity comma some y velocity, shows the direction and how fast we are moving in that direction. And that would be the length. It's how fast we are moving in that direction. Okay, we could kind of superimpose that into just an xy plane, which is what we do in vectors with vectors to kind of compare them. And just pop over there, right? And you could say this would be v sub t. We'll talk about calculating some things, but let's denote this v sub t. We'll actually use vector notation to denote its x characteristic and its y characteristics. And this kind of set of brackets will denote that we are talking about this velocity vector. Okay, so we will start with position. We'll get x of t and y of t position coordinates. Sometimes you'll see them as vectors, though I do not like to express position as a vector. It's more just like a location. But if you do, don't be confused. We know if we take the derivative of x, we get dx dt. Well, now we could also call that v sub x. And the derivative of y, dy dt, we could call that v sub y. And we can list it off together to talk about v sub t, our velocity at a specific moment in time for a two-dimensional particle having an x velocity and a y velocity. Okay, and then if we take the derivative again, we'll talk about acceleration. This is not new to us. The rate of change of position gives us velocity. The rate of change of velocity gives us acceleration. This would be d squared x over dt squared. We'll call this a sub x. D squared y over dt squared a sub y. And our vectors, we can look at a acceleration vector, or how quickly things are changing in whatever direction. A sub x comma a sub y. Okay, that's it. Just kind of new notation and just making sure we understand that we're talking about an x velocity and a y velocity. Some quick examples of that. We are given a position vector. I don't like to call it a position vector. Let's erase the vector. Let's use just regular parentheses saying, this expression will give us the position of this particle. Find the velocity vector of the particle at t equals 2. All I would do, understanding that this would be my expression for x of t, and this being my expression for y of t, is take the derivatives of both of them, giving me a v sub x of t, using your derivative rules. The derivative of log of t squared plus 5t is 1 over t squared plus 5t times the derivative of t squared plus 5t, using the chain rule. And then if I take the derivative of the y, I'll get a v sub y of t. And we can find both of these at 2. This would be 9 over 14. And this would be 12. And you'd list that off as a vector. V sub t at 2 is 9/14, comma 12. Okay? Mostly notation. That is new. Why don't you guys do this one? We got a particle moving in the xy plane, coordinates given by x and y, find its acceleration vector at t equals 1. The answer was 9/14, comma 12. Okay, we got a acceleration vector of 20, 24. Now, we may go backwards sometimes. We've been starting with position the entire time, and then asked to find velocity, asked to find acceleration. Sometimes we will just be given a velocity vector or acceleration vector, and we might be asked for a specific velocity or asked for a specific position. You do not have this question, you could please write it down. We have a velocity of a particle given by the vector 3t e to the t, comma 2t minus 1. We are given a position at t equals 1, 1, 2. That's an x, comma y position. Find the position at t equals 3. Okay, so starting with velocity. This is kind of going backwards. Okay, I wrote down this problem because this problem shows you the two ways that you can go backwards to find, positions given velocity. And this is just review. We've done both of these techniques before, so this is nothing new. It's just in this situation. You haven't seen it before. Okay? So, if I have velocity and I want position, what should I do? Right, you take the antiderivative, and that's usually our first kind of instinct. I'm going to say there's going to be two ways to do things. One, take the antiderivative. Don't forget to include a plus c, and then don't forget to find the plus c using information that's given to you. All right, so right here, this is a v sub x, and this is 3t e to the t. This is a v sub y, 2t minus 1. If I try to take the antiderivative of 3t e to the t, I'm not sure how to do that one. So let me come back to that. Maybe something in my memory will jog. Let's go to the v sub y. I can take the antiderivative of the vy, and that will give me an x, or not an x of y. It'll give me a y of t expression, right? A y position of my particles. And the antiderivative of 2t is t squared. The antiderivative of 1 is t. Don't forget a plus c. Now, you're told your position at time 1 is 1, 2. Well, that is telling me that my y position at t equals 1, so the 1 is here, is 2. It's also telling me, making sure you know this, is that my x position at time 1 is 1. Okay, I kind of don't like how these numbers agree with each other. Maybe change this to like a 3. Okay. At time 1, my y position is 2. At time 1, my x position is 3. Okay, great. Knowing that my y position at time 1 is 2, I can use that. Y of 1, which is 1 squared minus 1 plus c, that equals 2. C equals 2. I now have y of t is equal to t squared minus t plus c. Find the position at t equals 3. Y of 3 equals 9 minus 3 plus, that's a 2. Which is 8. All right, I got my y coordinate position, excuse me. Let's go back to this x velocity. Let's think about taking the antiderivative of that. I can't. You guys can't right now. There is a way to do it, but it's something that you'll learn in the future. So I need another way to find a specific position. I need another way to go backwards. discuss with your neighbors if you think you know what to do here. I give you a hint. You're going to have to use your calculator, okay, if you have a calculator available. This is, first method is the no calculator method. The second method we'll talk to you about is if you have a calculator. What would you do? No! Everybody thinks you should do. Plug what into your calculator? The Math 9? Your Math 9 does not give you an antiderivative. Math 9 gives you an area under a curve. Can't tell your calculator to take the antiderivative of something. But you will be using Math 9. Anybody? Yep, you will be using Math 9. If you recall, the fundamental theorem of calculus solved for f of b, an unknown value is equal to a known value plus the change in the function between a and b, which is equal to the area under the derivative function. Yep. Oh, they're not going away, bud. So, in this case, an unknown position equals a known position plus the area, or the change in my position. The change in my position is the area under the derivative of position, which in this case is my velocity. This is the most commonly used kind of formula, I'll say, on the AP exam. This is used more often than anything else. We see it year after year after year, this. So for this half of things, to find an x position, it's not always this, like the x is going to be this complicated and the y is going to be easy to do. It could be flip-flopped. Both of them could be complicated. Both of them could be easy. But for this situation, since I can't take the antiderivative of this, let's say I have my calculator. I want to find my x position at time 3. I have my x position at time 1. I will add the change in my x's, which is the area under my v sub x. Okay, and we use our calculator. I believe it's like something large. So 120.512. So 123.512. Okay, now we have our position. Our position is an x position, comma, a y position. Depending on the problem, depending on whether or not it's a calculator or a non-calculator question, will determine which one of these techniques you will have to use. Whether you should find C after taking the antiderivative, or if you should use your calculator and use the application of the fundamental theorem of calculus. This first example that we're going to do, we could use either method. If I said no calculator, you could take the antiderivative of both of these and find C. But let's say I did give you a calculator and say, hey, we don't have much time. Let's quickly find our position of our particle at time t equals 2. Do not say the position vector, just say the position at t equals 0 is 5, 0. No position vector, it's just where it's located. You get 9 and 4. Yep. Okay, now, could you do this by hand? Yeah, sure. Could you do this by hand? Sure. You just have to take the antiderivative and find the change in the antiderivative. I would not do this by hand, though. It doesn't make any sense. If I were to do something by hand, I would have just taken the antiderivative of this and found C. I would only be using this application of the fundamental theorem of calculus if I had my calculator handy, because it's quick and easy to find this using your calculator. Whereas the fundamental theorem of calculus to find the area under a curve can sometimes be a little bit tedious. Okay? I find that finding C a little bit less tedious. Okay, good. Next. If you're asked when is a particle that is moving in 2 dimensions at rest? Well, we've had questions like this before. When is a particle at rest? It's when what? Somebody shout it out. Yeah, velocity equals 0. But I have like 2 velocities here. I have an x velocity and a y velocity. So guess what? Our particles moving in 2 dimensions, they're going to be at rest when both of our individual velocities equal 0. Okay? Take this example. I'm given position given by an x equals and a y equals an equation, trying to figure out when this particle is at rest. You just need to find the velocity expressions for x and y, find when they're 0, and find when they are both equal to 0 at the same time. If they are never equal to 0 at the same time, the particle will never be at rest. All right, now let's actually graph this and see if we can see when graphing that a particle is going to be at rest. I haven't done this yet, but I feel like it's going to be interesting. So in your calculator, let's graph the set of parametric equations. It might shoot off at things. So if I plug in 3, who knows? It might be visible. I'm back in rectangular mode. I need to go back into parametric mode. t cubed minus 3/2 t squared minus 18t plus 5 t cubed minus 6t squared plus 9t plus 4. Yeah, it's gone. And it's gone. There he goes. Zoom out once. Beautiful. This is cool. So when you press trace, it goes. Now, unfortunately, our steps are by pi over 24s. I'm going to adjust my window so that I'm going by 0.2s. That way, we'll be able to see when t equals 3 right on the dot. Okay? So 2, 4, 6, 8, 1. 2, 4, 6, 8, 2. We see us come to the stop right at 3. And when you graphed it, it really was noticeable. It's like we're going to the left. Here's a location where we have a horizontal tangent. I don't have dy dt. That's when t was equal to 1, which we saw there. And then both of my dx and dy slowed down to the stop right by 3. And then we shot off in a different direction. Pretty cool. Now, we can talk more about how quickly we are moving in the direction or the speed of this particle. Again, this is from a previous example. I'm zooming this in at t equals 2. I already found v sub x was -3 and v sub y at time 2 was 4. So I had this x component and y component of my v of t vector. Okay, there's v of t. And we talked about the length of v of t showing us how quickly we are moving in the direction. Well, that is another way of saying it's the speed of our particle. Discuss with your neighbors how you think you could find the length of v of t. Go. Nope. So, if you said use the Pythagorean theorem and that length is 5, you are correct. Okay? This is how we kind of add vectors together. This is how we get that third vector and how quickly it's moving is it's actually, kind of connect one to the other. And since we can do that, we can see there is a right triangle created, and we can use the Pythagorean theorem. A squared plus b squared equals c squared. Okay? And solving for v of t gives us, and we will use this notation for the magnitude, v of t length. Another way of calling v of t's length is the magnitude of v of t. And mathematical notation, physics notation for magnitude is sometimes a set of two vertical lines. And that will just use the Pythagorean theorem. Take the square root of v of x squared plus v of y squared. Okay, it's that simple. So, here, number 11, says find the magnitude of the velocity vector. In AP problems, it will never be that obvious. Instead, they will ask you to find the speed of the particle at time t equals 5. So go ahead and do that. What's a 2/3 t cubed? Okay, that's simple. Now, we're going to do the first free response problem in your packet. However, since my copies all had the answers, I'd like you to just do it on the back of this page where you have this extra space. Okay. This free response problem was question number 2 from 2 years ago. Okay, it's an exact problem. You'll see that if you don't know what's going on, if you don't know how to find the speed, don't understand how to find the position, that this could be kind of tricky. However, out of all of the types of free response problems seen on the BC test, students wish that one of the 6 every year is a parametric equation question like this. I'd like you to see if you can do part A, B, and C. Read the question carefully, like always. Make sure you know what you're given, and then you can check your answers on your free response packet that I gave you that has the answers. Skip D. We do not know how to do D yet. It's not x of t. You are given dx dt. That's v of x. Part A, I need an x comma y position. If you just provided the x, you did not completely answer the problem. To find the x position, x of 3, that equals x of 0, which is 5, plus the integral from 0 to 3 under dx dt. You get 14.77. 377. Okay. Well, that's just the x coordinates. How do I get the y coordinates? This is the graph of y of t. When t equals 3, what is my y of t? It's -0.5. That is the position. Slope of the tangent, dx dt over dy dt. Well, we just need dy dt over dx dt. How do I find dy dt? The graph. Well, this is y of t. What would be dy dt? It'd be the slope of y of t. So the slope here is +0.5. So I'd have +0.5 divided by dx dt, and in my calculator, I'd plug in 3 there. Question, Mr. McLean?
Oh, yeah. I was asking if you assume that it's -0.5, or that you can check.
You can check because this line segment goes from 2, -1 to 4, 0. So it has a slope of up 1 over 2, slope of 1/2, or up 1/2 over 1. So yes. Don't always assume, always use the slopes given to you. Finally, the speed, just like we talked about, would be your square root of your v sub x at 3 squared plus your v sub y, which is 1/2 squared. This is the kind of stuff that we're doing, okay? Your homework is the remainder of the packet as well as some free response questions. Most of your tests will be kind of free response questions, so just let you know that. Start preparing for that. Test on Monday still. Not all of them. I don't know, just a couple I believe I assigned to you. Yeah. Yep.